Hi. In this video recording, we shall discuss how to evaluate the quality of a regression equation using R-square, adjusted R-square, Schwarz criteria, and cake information criteria. In any research article or a research thesis, after running the regression, we need to evaluate the predictive capacity of a regression model or to check the fitness of the model using R-square or adjusted R-square. So let's start from the evaluation of quality of regression equation. Before I start uh, uh, this lecture, I would strongly urge you to subscribe the channel so that you get the notification of all the upcoming videos. Lecture plan, as you know that after a regression is run and we have estimated the value of intercept and coefficient, which are collectively known as estimates or parameters. The heart and soul of any regression equation or any econometric model is to figure out how is the quality of the model. So evaluating the quality of model is very important after running the regression and after estimating the coefficients. The quality of a regression equation, or in other words, which can be called as evaluating the predictive capacity of a regression equation or explanatory power of the regression equation, can be measured with the help of R square, which is also known as coefficient of determination, adjusted R square, in which we adjust for the degree of freedom, Schwarz criteria, cake information criteria. So these four measures are used to evaluate the quality of a regression equation. And after we discuss these four measures at the end of this recording, we shall discuss how some researchers misuse the value of R square when they only try to increase the value of R square and they forget about the economic theory. So let's start from the working of the R square. So the first equation is basic regression equation in which y is dependent variable, beta naught is intercept or constant, which tells us the value of dependent variable when our independent variable is equal to 0. Beta 1 is called the slope coefficient, which measures the change in a dependent variable due to 1 unit change in independent variable, and epsilon measures the error term. If we write this equation in variance form, so here we are having the total variance of the dependent variable is yi minus y bar square and then its sum. So this side, this is the total variance of the dependent variable. Now it is being decomposed or divided into two parts. This part is part which has been explained by the independent variable. Beta naught plus beta 1 into x is known as y hat or estimated value of the y. So the variance of dependent variable is equal to variance of the estimated variable plus variance of the error term. So we have just converted our basic regression equation into variance form. In the regression equation, we will see it that y is equal to estimated y plus error term. And here in the second equation, we will say that variance of the total dependent variable is equal to variance of the estimated y plus variance of the residual. Basic formula requires that we should have done e I minus e bar, but we assume the mean of the error term to be equal to 0. Thus, we have not written here e bar and we have simply and directly written that sum of e square, which is error term. Now, as this is the total variance of the dependent variable, so we call it total sum of square, in short written as TSS. Why are we calling it total sum of square? Because this is total variance of the dependent variable, and variance is square of sum of the square of deviation of each value of y from its mean. So that's why we call it total sum of square. Now, some part of this total sum of square which has been explained by independent variable, that is called explained sum of square, in short written as ESS, and the remaining part of the dependent variable which could not have been explained by independent variable is the residual sum of square. So total sum of square will be equal to explained sum of square plus residual sum of square. Total sum of square is the total variance of the dependent variable, and it has two components. One component which has been explained by independent variable is called ESS, and the remaining component which depends upon variable other than the included variable x is called residual sum of square. Now in this equation, higher the portion of explained sum of square will be, better will be the equation. So we calculate how much percentage of total sum of square is ESS. So we simply in the calculation of R square we put ESS divided by TSS. So answer will tell us the percentage of total variance which was explained by the independent variable. So as ESS is equal to TSS minus RSS, therefore it can also be written mathematically like 1 minus residual sum of square divided by total sum of square. Now we have already written that residual sum of square is equal to sum of E square. So we just write it 1 minus sum of E square, and total sum of square we know that that is equal to sum of y I minus y bar raised to power 2. So the final formula of R square is 1 minus sum of E square divided by sum of y I minus y bar square. As we know that in brief, ESS divided by TSS is R square, so its value will lie between 0 and 1. So it will be equal to or more than 0 as in a regression OLS method, and R square will be less than 1. So range is between 0 and 1. The higher the value, the better the equation is. For example, if we get the value of R square 0.7, we shall say that 70% of the variance of dependent variable has been explained by independent variable. And if we are getting the value of R square equal to 0.10, we shall say that only 10% of the variance of dependent variable has been explained by our independent variable. So its value lies between 0 and 1. Now, R square can be used to compare the performance of two regression equations only if they have the equal number of independent variables. If number of independent variables is different in different regression equation, then R square will not be very useful measure, because the equation having higher number of independent variable will be having higher value of R square. It does not mean that an equation with higher number of independent variable is stronger than the equation having less number of independent variable. The new variable, new predictor variable, when added to the regression equation, they are very likely to increase the value of R square just by chance. Therefore, when we have to compare the quality of regression equations having different number of independent variables, then we prefer to use adjusted R square instead of R square. So the formula for adjusted R square is 1 minus residual sum of square divided by n minus k minus 1 whole divided by total sum of square divided by n minus 1. So we are adjusting the residual sum of square by dividing it into n minus k minus 1. So if you look carefully, k is number of independent variable. So higher the number of independent variable will be, the lowest will be the value of adjusted R square. So thus the number of independent variable which was increasing the value of R square, they have been punished now by this formula. Now we if put bigger value of k in this equation, our result will be will become lower. So again, R-square is used to compare the quality of two regression equations or more than two regression equations only when all those regression equations have same number of independent variables. If number of independent variables is different in different equations, then we compare their quality on the basis of adjusted R-square instead of R-square. Now here we have a regression example. Here on left side we have a simple linear regression in which we have one independent variable, and on right side we have a regression equation which is multiple regression analysis because it consists of more than one independent variables. Now let's discuss what are these variables. Dependent variable in both of these equations is income growth, which has been measured as annual growth in per capita income. Beta naught, as you know, is intercept in the equation which shows the value of dependent variable when independent variable is equal to 0. Beta 1 is the slope of coefficient which tells us by how many units dependent variable change due to 1 unit change in independent variable. HE is the health expenditure and has been measured by the percentage of GDP spent in health services. AE is the access to electricity measured by the percentage of population which have access or which is using the electricity, and our mu I is the residual. I indicates the nature of the data is cross sectional. So theory says that higher will be the health expenditure, higher will be the income growth, and higher will be the access to electricity, higher will be the income growth. Thus, in both of these equations, beta 1 and in this equation beta 1 as well as the second beta which I could not write here, beta 2, both will be having a positive relationship or a positive effect on the income growth. Now, as these two equations have different number of independent variables. The first equation is having one independent variable while the second equation is having two independent variables. Therefore, we cannot compare their quality with the help of R square. We will have to use now adjusted R square. Now this is their result of those regression equation here, and we have only one independent variable, health expenditure. Its R square is 0.4125, which indicates that 41.25% of variance in the annual income growth has been explained by our health expenditure variable. In the second equation, as we have two independent variable and their R square is 0.7125, so this value shows that 71.25% of variance in the income growth, which is our dependent variable, has been explained by two independent variables, which are health expenditure and access to electricity. But as these two equations have different number of independent variables, therefore we shall use the adjusted R square to compare the performance. We shall not say that second equation is better because it has higher R square. We shall say that second equation is better than the first equation because second equation has higher adjusted R square. Because adjusted R square of second equation is 0.4523, which is higher than the adjusted R square of 0.1523. So this is very technical point that when is R square used and when is adjusted R square used. In this case, when two equations have different number of independent variable, we shall use the adjusted R square. Now here we have some explanation about R square. R square is proportion of variance in the dependent variable, which is growth in per capita in our case, which can be predicted from the independent variable, and this value of 41.25% of the variance income growth can be predicted from the variable health expenditure. Please note that R square is a measure of overall measure of strength of association, and it does not reflect the extent to which any particular independent variable is associated with the dependent variable. R square is also called as the coefficient of determination. Now, as far as adjusted R square is concerned, as predictors mean independent variable, our x variables. are added to the model, each predictor will explain some of the variance in the dependent variable simply due to chance. One could continue to add predictor to the model and R square will continue to increase, but it doesn't mean that equation will be better because of higher R square. When the new variable are added into the equation, R square will definitely increase. So when the number of observation is small and the number of predictor is large, there will be much difference between R square and adjusted R square. However, if the number of observations is large compared to the number of predictor, that so when the difference between R square and adjusted R square will be high and when the difference between R square and adjusted R square will be low, it depends upon the number of independent variable in the regression equation. If the number of observation is small, which is n, that is small, and number of predictors, which is number of independent variables, in the formula we measure it by k, is large, then the difference between R square and adjusted R square will be much higher. And if the equations are having different number of independent variables, we shall prefer adjusted R square as a measure of quality of regression equation over R square. By contrast, when the number of observations is very large, n is very large compared to the number of predictors and k is very small, then the value of R square and adjusted R square will be much closer to each other and there will be no big difference between the values of R square and adjusted R square. For example, if n is equal to 100 and k is equal to 3 in one equation and is equal to 4 in the second equation, then 100 minus 3 will be 97 and 100 minus 4 will be 96. So there will be no huge difference between 96 and 97. Now, after we evaluate the regression equation and when we run regression in Microsoft Excel or eViews, we get this output which is known as analysis of variance or ANOVA. It measures the overall fitness of the equation. F is a measure of joint hypothesis testing, and if it is significant, it means that our included independent variables overall have relationship with the dependent variable. And if this value is bigger than 0.05 or 0.1, whatever our level of significance is, then we say that overall regression model is not significant and we do not study the individual coefficient and their significance. So the p-value associated with this f-value is very small. So if you get the ANOVA result like this, so this is the p-value 0.000, which is very small. And these small values indicates that overall our model is fit. Because these values answer this question, do the independent variable reliably predict the dependent variable? If answer value is less than value of this significance is less than 0.05, we'll say that yes, our independent variable reliably predicts the dependent variable. And if this value is higher than 0.05 or 0.10, we shall say that our independent variable do not have reliable prediction capacity as far as dependent variable is concerned. So it has, I have already explained that p-value is compared to the level of significance, which is typically 0.05. And if smaller, you can conclude yes, independent variable reliably predict the dependent variable. If p-value were greater than 0.05, we would say that group of our independent variable does not show a statistically significant relationship with the dependent variable, or in other words, the group of independent variable does not reliably predict the dependent variable. In addition to R square and adjusted R square, two other measures which Microsoft Excel as well as eViews report are archaic information criteria. In short, this is known as AIC. and Schwartz criteria (SC) are also widely used measures to evaluate the quality of regression equation. However, opposite to R-square and adjusted R-square, the lower the values of AIC and SCR, the better the fitness of model is, and vice versa. If difference between AIC of two model is equal to or more than 2, then we say that there is significant difference between the fitness of two models. And whenever we run any regression model in Excel or in eViews, both of these software provide us this all the four measure R square, adjusted R square, archaic information criteria, and Schwartz criteria. Now let's move to eViews, and we can see this example which we just discussed in the PowerPoint slides. So let's run the regression by typing word estimate in the command window. So our dependent variable was per capita income growth. We select it, space C, space our first variable was health expenditure. So we'll select it. Now if we run this regression, we can see that in this regression output, our intercept is 7.32, which tells us that uh, per capita income growth will be 7.32% if expenditure on the health sector is 0. Our slope coefficient indicates that uh, this relationship will be negative, that income growth will be 1.37% lower, will decrease by 1.37% if the health expenditure increase by 1%, which is against the theory, but because we are having only 20 observations and very small sample, so this is possible to get such against the theory signs. The R square value is 0.71 while the adjusted R square value is 0.12, and the Schwartz criteria of this equation is 6.12 and the cake information criteria is 6.02. Now we shall run the regression by adding one more variable in the equation, which was access to electricity, and then we shall see how our results are. Let's save this equation. Let's say we save it EQ01, and now we shall re-estimate the equation by adding one more variable, that is access to electricity. Okay, now we have run this equation and our R square is 0.18, while in previous case our if we can open these two windows together. Let me open this window as well. Okay, at one time one. So here R square was 18%. No, EQ01. Okay, let me save this file. First of all, name EQ02. Okay, so if we at one time probably this is equation 2, and if I estimate it with one variable, so here R square is 0.717 and here this R square is 0.12. But if we open the so this is equation 2. So previously it was having the R square of, if we add the two variable, it was at having the R square of 0.18, while adjusted R square was 0.09. Okay, so our second equation was not better than the first because of having higher R square. Our second equation was poor than the first equation. When the first equation adjusted R square is 0.12, while in the second equation it was 0.09. We can rerun and I'll show you again. Access to electricity. We add this variable. See here, our adjusted R square has decreased from 12% to 9%. So it means that the first equation was better, although the R square of this equation is higher than the R square of the first equation, But as first equation was having one independent variable and the second equation is having two independent variable, we shall use the adjusted R square. Adjusted R square of the first equation was higher than the second one. So on the basis of this adjusted R square, we shall conclude that our first equation was better than the second equation. Now moving towards the AIC information criteria in Schwartz. Here we have 6.10 and 6.25. Now rerun and see how was these values without access to electricity. See here again, because then we will not see 6.10 and 6.25. And now here we are having 6.02 and 6.126. So on the basis of archaic information criteria and Schwartz criteria, both of these equations are more or less same, and there is no significant difference between the equations, because as we said that here that if the difference between AIC of two model is equal to or more than 2, then there is a significant difference between the fitness of two models. But in two of the equation which we just run in the A-views, the difference was very nominal, even less than 1. So we'll say that on the basis of AIC and Schwartz criteria, both of the equation were more or less same as far as their quality is concerned. Now, the last and very important point is that researchers, while they write the research paper or they write their thesis, they pray for the higher value of R square, and sometimes they try to maximize the value of R square, and they forget the economic meaning or economic sense of relationship between independent variables. Therefore, they sometimes misuse R square. Higher R square is a good thing. Higher R square is not bad if theoretically justified relationships are found in the equations. However, if the relationships are not theoretically justified in the equation, then higher R square values become meaningless. See these two equations. In the first equation, dependent variable is water demand, independent variable is price of the water, population and rainfall. Higher the price will be, lower theoretically lower will be the water demand. Higher the population will be, higher will be the water demand. Higher will be the rainfall, lower will be the water demand. The second equation does not have price as independent variable. It only regress the water demand on population and rainfall. The adjusted R square of the first equation is higher than the adjusted R square of the second equation. So if we purely decide on the basis of adjusted R square, then obviously we are going to conclude that our first equation is better than the second equation. But in reality, it is not better. Why? Number one reason, price may not be an appropriate independent variable as far as water demand is concerned, because water is a necessity good and it may not depend upon the price. It is in price insensitive or demand is inelastic. So price variable should not have been there, while if it has been included, it it is not theoretically justified. The second mistake or second problem with the first equation is that even if we include the price variable in the water demand, how can we justify the positive relationship of price with the water demand? Because according to this equation, if price increases, water demand will increase, which is against the theory, against the law of demand. Law of demand states that keeping other things constant, if price increases, the quantity demanded decreases. So this is against the theory. So although the first equation is having the higher value of adjusted R square than the second equation, but we shall still prefer the second equation because number one, it does not include the price, and on number two, because the coefficients of independent variable are exactly according to the theory, while in equation 1, the coefficient of price is opposite to the theory, is against the theory. Therefore, this is very important for the researchers and for the students who are supposed who are expected to write their research papers and thesis, that while their effort to maximize the value of R square, they should not underweigh the theory. They should not ignore the theory. If the signs are according to the theory and significant and value of our adjusted R square is higher, very fine, we are happy. But if the found signs are against the theory and we purely decide on the basis of adjusted R square, that will be wrong decision. Thank you.